different types of motion here. We're going to start with simple harmonic motions. So recall that the ideal spring force is given by Hooke's law. We've seen this before. Where the force of the spring, I'll put the little s there for the force of the spring, is equal to negative k times x. You guys remember what that k represented?
Spring constant.
That was the spring constant, not kinetic energy. This K is your spring constant. Remember this minus sign here was just to tell us that this spring force is what we call a restoring force. So we were thinking about the force on the spring, and I can attach a mass to it, which we'll see this mass kind of moving back and forth later on. But if I pull this out, and my x is positive, then my force is a restoring force, bringing you back to equilibrium over here. So if my x is positive this way, then my force is negative that way. That would agree with this equation here with the minus sign. If I was using x this way, negative, to the left of my equilibrium point, then my x would be negative, and my force would be positive. That just says here, this minus sign is telling us that my force and my displacement are in opposite directions, because it's a restoring force. I pull out this way, it wants to pull back in this way. That's what the minus sign meant. And you might remember I said, and we even saw it in our lab, I think, where they wrote it down without the minus sign. In terms of just the strength and magnitude of that force, we can just say the size of that spring force is just k times x. And the minus is there really to kind of remind us that it is a restoring force back to equilibrium. But when we actually use that equation, we can leave that minus sign off in many cases because we'll just be looking for the magnitude. And we haven't used that a whole lot. We did a little bit in lab, we saw the behavior of that, we graphed it. And here again, we're not going to deal much with that equation itself, but it's the equation that describes the force of that spring right there. Okay. Motion under the influence of that kind of force is called simple harmonic motion. Sometimes we'll use an SHM for simple harmonic motion to shorten out a bit when we're writing it out. Okay. Now, most of our simple harmonic motion is going to be a mass on a spring like this. There are some other situations where we can describe harmonic motion of something like a pendulum or other objects that are going to oscillate back and forth. But we're just really going to look at this case here to start with. And this equation, you're really not going to have to use a whole lot. Okay. We're going to look at the motion of a mass on this spring now oscillating back and forth. Whereas before, when we dealt with our springs, we were looking at the potential energy stored by that spring, we were looking at the force of the spring, but we weren't really looking at the motion back and forth. We'll let a mass slide this way maybe and then collide with this, and then the spring would be compressed a certain distance, and we knew it was going to go back. But a lot of times with energy, we just stopped there and said, well, how far does the spring get compressed? Now we're going to say, well, if I stretch this out here, and here's that equilibrium line, maybe I pull it out here some distance and I let go, what's going to happen? When I let go, what happens to the mass? It goes back this way. Does it stop right here? No, it's going to go back here. That's going to oscillate back and forth. Okay. Now we're going to look at that kind of motion. So, the motion of the spring, or this mass on the spring, going back and forth like this, can be described graphically with a sinusoidal equation of motion, which basically just means it can be described by a sine or a cosine function. Now this is a different form of the sine or cosine than you're used to. We've been dealing with sine and cosine for just simple right triangle trig. Okay? But the sine or cosine math function as a graph just looks like this. And those of you who had trig or some other math might know that. But the graph of sine or cosine has this behavior here. We've been looking at sines, cosines, and tangents for just simple right triangle trig. Okay. And those ratios of the opposite of our adjacent or opposite of our hypotenuse, we're only working for right triangles. But the functions themselves work all the time, and they give you graphs that behave like this. Okay? That's what we mean here by a sinusoidal equation of motion. The equation of motion for this mass on a spring in this case looks like that. Okay? This is the mathematical description of this motion that's going back and forth. Okay? And this is going to take a little time for you to kind of wrap your minds around because it feels different. When you look at a graph like that, you're going to want to say, well, this looks like I'm going up and down. Because physically to draw this, I went up and down like this. But we're not going up and down. We're going left and right. Or I can use a graph like that to describe the oscillatory motion here of the mass going back and forth. This does not mean that I'm moving up and down. This just means this is my displacement or my position versus time down here on the x-axis or the horizontal axis now. So what this graph is showing is the position of the mass over here as a function of time. But it's not showing the path of the mass. So don't confuse this with like a path of your trajectory. This is just going back and forth like this. Okay? So this would really be, with this graph here, this would be like x in meters up here on the vertical axis. Okay? And so if I'm starting right up here, then where would I be in the motion over here? What position would I be at in the spring, letting it go back and forth? But at which location on this picture over here would we be if we're right here on the graph?
Compressed.
So to the right over here, at our maximum displacement. So I pull it out here, and there's no friction or anything else here, and I let it oscillate back and forth. It will always, what we say, damp out in reality, and it's going to stop eventually. But let's assume now we're going to oscillate back and forth with the constant amplitude the whole way. Okay. And that means we're starting right here at this point. Okay. Where are we right here? Then that means we came back here. Then what happens physically with mass over here? It goes back this way, right? So now it's going to go back down to this point. Then it comes back here to this point right here. And then it comes one more step back out to where it started from here back to here. That is one complete cycle. From here into here and back to where I started from. That's from here to here. Or from peak to peak would be one full cycle on here. We're going to start looking at those properties of this motion. And this looks like a wave, right? Something that's waving. But this is just a mathematical description of this right here. Okay? If I take this chain over here and I go like this, I can make a wave, right? This is a real physical wave that has properties of a wavelength and an amplitude and a frequency. That would be describing a real physical wave on a chain or a string or something. This is just a way of describing this motion. But they're going to be very similar properties that we have for both. But they're just kind of describing two different things. Okay? So on here, this is going from here to here, one full cycle. Okay? And the time that it takes to make one complete cycle is what? What do we call that? Period. So we're going to have terms like period and frequency. The amplitude is your maximum displacement from equilibrium. So that would be like, if this was my maximum displacement over here, that we would call that A. I'll write all these down in words for you so you have just complete definitions for them all. But that's what we're talking about here, where on this graph you'd have an A here and a minus A over here. And your maximum displacement from that equilibrium is what we call the amplitude. Okay. From here to here is one complete cycle. From peak to peak, or trough to trough, or really any two consecutive points, like from here to here, this whole segment from here to here look at that pattern here, from here like this, you can see that as one full wave right there in between my hands right here. Okay, so you'll need to be able to look at these graphs and identify properties like the wavelength, the frequency, know what we mean when we're talking about a full cycle or a half or two of them or something like that. But this graph here describes that motion. Okay. And remember, this is just describing motion that's going back and forth like this, or if you imagine being on a spring like this, where I had something like this, where this was maybe my equilibrium line down here, and that was my equilibrium length. I'm looking kind of top down on a table. If I took this thing, I let it go, it's going to oscillate up and down. And if you imagine the board moving, or me moving with this, it's going to make this graph, right? If I just held this here, and it's going up and down, this is like a wheel of paper here, going through, this is moving, as this oscillates up and down, it's going to make this graph here. Okay? That's what we're using this graph to describe, just the one-dimensional oscillation here, but it looks like this because we're counting on over here with time. You guys see how that works with why we can describe this motion with a graph like that? We're not going to look at the equations of motion for that, which are actually sine or cosine functions, not the same opposite over adjacent rules that we've been using before, but they are actually sine or cosine functions. You will see those functions in your book, but we're not going to use them. So just understand what the graph looks like and its behavior, but not the functions that we use to describe those.